So circuits always fighting themselves. It's a transient condition. It doesn't last forever, but it's ultimately it's a thing that limits current flow. Your maximum current value is what gets limited by this self-inductance within a circuit, right? So previously, sounds like a TV show, we had found that magnetic flux could be written as inductance times current, conventional current, meaning current flow in the direction of the electric field, which isn't real. Current electrons go the other way, but we have conventional current. We also had that an induced voltage was the time rate of change, the negative time rate of change of that, which really just works out to be minus L di dt. So that's some old news. Now I do want to kind of extend our views a little bit here today, extend/remind us of what we did. Inductance is a geometric thing when it comes down to it, which really shouldn't be. It's a function of geometry, just like resistance was largely a function of the dimensions of the conductor that we were dealing with. So this is Faraday's law here. Going back a little bit. So if I have an inductive circuit, so I'm just going to build a solenoid here, and so we're just going to pretend that it's connected to a voltage source. And so we'd have, current flowing through it. This coil, there would be some radius that coil has. A coil is a round thing, cylinder. It has a radius, all right? It has some number of turns, N, big capital N. We use that for the number of turns that it has. And then it has some length, okay? So there's a length of this coil, number of turns per unit length. That's the little n in Ampere's law. Mu naught I, all right? And so just sort of some basic stuff there. So in fact, the B, or the magnetic field, would be mu naught I N per L. And so that's the number of turns per unit length. So that's a little bit of review stuff. So what happens is this boils down to remember flux? Flux always ends up being an area times field business, because it's how many of those force fields zoomies are going through some cross-sectional area. Sorry for the high-tech terminology, right? But I do have to keep myself entertained as much. So there's this area business, and I write n pi r squared because there are some number of those pi r squareds. And so even though they're stacked, they still add up, because every loop has this flux effect. So they have to add up. Even though you'd think, oh, well, shouldn't they be spread out so they're contiguous with one another in a plane? No. Yeah, I keep stacking. All of these laws are per loop, every last one of them. And so when you have more than one loop, you have to throw the count in there, all right? Capital N. And some of them, the original form of this was mu naught n I, little n, and that's where little n is number of loops per unit length. That's where that comes from. So sorry for not mentioning that. And so this area bit here. That's what, just remember it's always an area times field, so that's sort of old news. And then I have the I in per L. And so basically, we would work out flux, which is largely an area geometric business, and if we were to, and we went over, I think I showed this formula today, inductance would have this form, self-inductance. Now notice here.
Is that pi r squared?
Yes. That pi r squared, that's an area. That's a cross-sectional area for a cylinder because coils are cylindrical. A number squared is just obviously a unitless number, but then length is another geometric property. And so all but this fundamental constant of the universe called magnetic permeability of free space is entirely geometric. So one way to understand this statement of inductance here, okay, you have all of this geometric stuff, okay, and then you have mu naught. So again, whether it's mu naught for magnetic permeability or epsilon naught for electric permittivity, these are fundamental constants of the entire universe that describe quantitatively the capacity of space to tolerate either an electric field or a magnetic field. Call it the thickness of space for those fields. That would be a conceptually largely correct viewpoint. All right? As a medium, space presents some sort of limit to things that propagate through it. Empty space has the least limits. And if we saw with dielectrics that solid material increases that factor, makes it harder for things to propagate through it, and ends up just scaling it up as opposed to being a different constant, just a scale factor of the fundamental constant. All right, so self-inductance, revisited, because we did talk about it when we introduced inductance the other day. And so just wanted to go back to that a little bit before we deal with a loophole, so to speak, in Kirchhoff's loop rule. All right. So let's, and by the way, inductance is often very close to zero, but it is never zero. Every circuit has inductance. Okay? Every circuit has some amount of inductance. But let's get ourselves a circuit here, and so here's an inductor and a resistor and a battery. So V for voltage, L for inductance, R for resistance. So if I close this switch, all right, and current starts flowing in the circuit, at time zero, current will be zero. All right, at that very instant, we don't have any flow. We've just opened the floodgates. It's just that instant before everything starts to take off. At a time, sometime greater than zero, correct my Lenz's law, thing I just had you play with the demo toy, leads to some sort of resistance to change. So basically, the inductance of the circuit is going to fight current flow by producing a magnetic field that induces a voltage that slows that down. Just like you saw with those falling loops. Same basic thing just you can't eyeball it. All right? Now, we should be able to note that if I just plotted current versus time, all right, I know that this resistance, well, it's going to lose, okay? And by the way, an inductor essentially has zero resistance. It's essentially, it might as well be a superconductor, even though you're not going to get superconducting properties out of that hunk of metal, okay? It has no resistance, all right? It's just this inductance thing. So I know that eventually current is going to reach a maximum value. And that maximum value is going to be Ohm's law, V over R. Current will equal voltage over resistance, okay? You wouldn't even need to have your brain engaged fully to know that, well, current's going to get to a maximum value, all right? And inductance is something that changes the rate at which we get to that maximum. So we're going to have, without a doubt, we're going to have an inductance curve, and we showed the math the other day for both capacitors and inductors. They're basically exponential functions of E, and so they have this characteristic shape for build-up and the flip of it for decay. So if I have a high inductance, that's going to make the resistance, okay, so this will be a high value of inductance. But if I have a low value of inductance, okay, then it'll get to the max faster, right? Duh. This should be a no-brainer for people with your mathematical background, all right? If somehow there could be zero inductance, then it would just instantaneously go to the max. So I do want to, I'll draw it here. This would be L equals 0, which is impossible. Now, there's a first 3 weeks reason, week 2 or 3 reason. If you didn't know anything about inductance, you would reject there being a change that's instantaneous. Every change requires time. Every change, not just a change in position. Okay? But underneath the hood of this is the change in position of, guess what? Free electrons. They can't change their position instantaneously. Therefore, none of these effects are instantaneous. They always require time. And so even if I didn't know anything about inductance, I just knew it was a thing with these behaviors, I would immediately reject that it was possible to have zero inductance. Inductance is always present in a circuit. And the textbooks are probably misleading at best and wrong at times, because they ignore this, or they'll even show it, what I'm about to show, as an evidence of Kirchhoff's loop rule, and technically it's not, even though it really looks like it is. So we'll get to that well here shortly. So let's so Kirchhoff's loop rule says the sum of voltages around a loop is 0. Now, the assumption is that it's a loop of that it consists of something other than voltage sources only, all right? And this rule is just mostly true. Kind of think Princess Bride is mostly true, all right? There is always going to be an induced EMF, electromotive force, because inductance cannot be zero. So this would mathematically, there's going to be, the fact that this can't be zero means that there's always an induced voltage, okay? When you run a circuit. So let's kind of remind ourselves of Faraday's law here. That tells us a changing magnetic field, or a time rate of change of magnetic flux changing, which is obviously related to the magnetic field, is minus the inductance times the time rate of change of current. Recent development for us. So let's get us the circuit going again. Same circuit as before. Inductor, resistor, so voltage, etc. So we close this switch, plus here, minus there. That means the electric field is going that way in the battery. We're going to have current, conventional current, flowing this way around the block. The electric field through the resistor is also going to be in the direction of current, because we're talking about conventional current. Remember the current density business? The direction of the electric field is always the direction of conventional current. Obviously the electrons are going the other way. But we're not talking about electron flow. We're talking about what engineers would call whole flow, or just conventional current. All right? Thank you, Ben Franklin, for that. So you would think, oh, I'll use Kirchhoff's loop rule. Well, I'm not going to use Kirchhoff's loop rule, because Faraday's loop rule is the right answer in this case. And so the sum of all of the voltage drops, remember, electric field is force per unit charge. A little chunk of DL is a distance. Force times distance is work. EDL is work done per unit charge. It's voltage. Okay? It's voltage. So I'm going to sum all these things up. There's the electric field here, 0. Going around this way, there's going to be an IR drop through that resistor, because I'm going downhill with the field. And there's going to be, when we come back around up through the battery, there's going to be a plus V. And according to Faraday's loop rule, nobody calls it Faraday's loop rule. I'm calling it Faraday's loop rule to poke fun at Kirchhoff, because he ain't here. He can't do anything about it, all right? It's got to equal L di dt. This looks like Kirchhoff's loop rule because it's got a 0 in it. If I could rearrange this so that it equals 0, and you think, oh, Kirchhoff's loop rule, and I did a loop. Nope, not Kirchhoff's loop rule. It's Faraday's law. Faraday's loop rule. It is a loop rule because it deals with a path or a surface, if it's a surface. Okay? This is a subtlety. All right? Admittedly. It's a subtlety that generally only matters deeply to the physicists. It is material to the electrical engineer, though, because you're going to need to pay attention to these things on the transients. So in between transients, the pie in the sky loop rules of Kirchhoff are perfect. And that's generally what you're concerned with. Transits will present new challenges that you'll analyze slightly differently, and you'll add it all up and account for that as you move forward. So I got to advance my screen here. Because it can look like a loop rule mathematics, then it must be a loop rule application. And to finish the deal on this, so what that'll boil down to is V minus L di dt equals IR. Now I want to point out to you that what do I have here? I have voltage this is essentially, this part here is Ohm's law, which shouldn't be called a law because it's not always true. Things get hot, it stops being true, all right? But it's mostly true. There's this little inductance factor that we just showed graphically is a short-term thing, all right? But this is essentially, if I include Faraday's law of induction, Ohm's law becomes a real law. This applies all the time. Because as soon as current stops changing, if that equals 0, if current flow stops changing, getting bigger or smaller, then that differential goes to 0 and that term drops out and you just have V equals IR. So this would be, I haven't seen this in a book yet where they point this out. Of course, I only have maybe half a dozen or 8 physics textbooks on my shelf, so I clearly don't have them all. But the ones I have are some of the longest running, most successful books, and some of them are new. I haven't seen it. And I missed this during my education. This went past me while I was still in college. So found out later. I'm like, oh yeah, duh. You know, it's all there, but a lot of textbooks mistake the fact that this thing back here, technically not, but in the end, does it really matter much? Practically no, theoretically yes. All right, so, but I wanted it to give you that for just for grins, because we could and we should. So